Hey everyone, welcome to today's Explainer. I am absolutely thrilled you're joining me because today we are going to demystify something that honestly feels like pure magic. Have you ever stopped to wonder how digital storage actually functions? Well, by the end of this Explainer, we're going to completely strip away the complex jargon and reveal the incredibly simple physical mechanics at the core of all computer memory. We're getting right down to the secret of zeros and ones.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the digital mystery, move into a light bulb analogy, and then translate that into hardware reality. From there, we'll see how those hardware concepts create text and ASCII, construct pixels and images, and finally, we'll look at the massive scale. I promise you, starting with a simple analogy is going to lead us straight to understanding some seriously complex modern tech.
All right, part one, the digital mystery. You know, we use these incredibly complex devices every single day. Laptops, tablets, our smartphones, but most of the time, we don't truly understand what goes on under the hood. We just tap a screen, and boom, a whole world appears. The actual mechanics remain totally hidden from us. Which leads us to this really fascinating question. How do all the books you could ever read in an entire lifetime fit onto a single tiny memory chip? And it's not just books either. Think about it for a second. Your photos, your favorite music, movies, bank details, even your passport and medical records. Almost everything about you now lives right inside your phone.
But when we compare the physical world to the digital world, the mystery really deepens. In the physical world, we use all sorts of vastly different materials for our data, right? We've got paper for books and passports, actual physical folders for medical records, vinyl or tape for music. But in the digital world, all of that incredibly varied information is entirely stripped down and translated into just two numbers, 0 and 1. So, how can just two digits represent such a massive variety of complex human data? That is the core mystery of the binary language.
Moving right along to part two, the light bulb analogy. To solve this digital mystery, we're going to use a really simple, relatable building block. Let's play a game. Imagine you're standing on a quiet road, and your task is to count how many cars pass by in exactly 1 hour. But you aren't given a notebook or a pen. Instead, you're given just 4 light bulbs, and each one has its own simple on-off switch. At the end of the hour, someone's going to look at those bulbs, and they need to know exactly how many cars passed. Now, the obvious first method is to just switch on one bulb for the first car, the second bulb for the second car, and so on. But as you can quickly see, that only lets you count up to 4 cars. Once all 4 bulbs are on, you are literally out of memory. If a 5th car passes, you have absolutely no way to record it. So we're going to need a smarter method. This brings us to the second method, combinations. Instead of one bulb equaling one car, we look at the states of all 4 bulbs together. It's like a giant puzzle. If you systematically flip the switches on and off in different patterns for each car that passes, you create a code. If all bulbs are off, that represents 0. When the first car passes, you turn on just the first bulb. For the second car, you turn the first bulb off and the second bulb on. For the third car, you keep the second bulb on and turn the first bulb back on. The real aha moment here is that 4 bulbs, each with 2 states, on and off, give us exactly 16 distinct combinations. That's 2 to the power of 4. Which means, with just 4 simple light bulbs, we can perfectly record and read any number from 0 all the way up to 15.
Which brings us to part 3, hardware reality.
Okay, let's shift gears from our analogy to actual computer hardware. Now, what's really interesting about this is the revelation that computers do not have physical numbers, like literal zeros and ones, floating around inside them. What they actually have are these microscopic components. First up is the capacitor. You can think of it as a tiny device that temporarily stores an electric charge. Actually, scratch that. It's more like an incredibly fast miniature battery. But a battery needs a switch, right? And that's exactly where the transistor comes in. It's an electronic switch that controls the flow of charge right into or out of the capacitor.
So let's connect the dots here and tie our building blocks directly to our game. In our analogy, a glowing bulb was a 1. In reality, a fully charged capacitor is a 1. An unlit bulb was a 0. And inside the computer, a discharged capacitor is a 0. And while we used our own hands to flip mechanical switches for those light bulbs, the computer uses that electronic transistor to quickly charge or discharge the capacitor. It is literally the exact same principle, just executed on a microscopic level.
All right, let's build this computer's memory step by step. Step 1. When you pair one capacitor with one transistor, you get the absolute smallest possible unit of memory. We call this a bit, and remember, each bit can only exist in one of two states, charged or discharged, meaning 1 or 0. Step 2. When we group 8 of these bits together, we form what is called 1 byte of memory. Millions of these capacitor transistor duos working together are what we specifically call dynamic RAM.
Next up, Section 4, Text and ASCII.
So you might be wondering, how on earth do we take these tiny charging batteries and use them to represent something like complex human language? Well, it all comes down to the math. We saw earlier that 4 bulbs gave us 16 combinations, but we just learned that a byte of memory uses 8 bits. So if we have 8 bulbs or 8 bits, we calculate 2 to the power of 8. That gives us 256 distinct combinations. That means 8 tiny capacitors can represent any whole number from 0 to 255.
So, the crucial point is how we actually assign meaning to those 256 numbers. This is done using a universal standard called the ASCII code. According to ASCII, every letter, number, and punctuation mark gets a unique number between 0 and 255. Take the capital letter A, for example. Its ASCII code is exactly 65. When you hit a capital A on your keyboard, you are physically commanding the computer to take a byte of memory, 8 tiny capacitors, and switch them into a specific on-off pattern that translates to 65. That binary pattern is 01000001. Those exact charges and discharges equal exactly 1 byte, and that becomes the computer's physical version of the letter A. So if you type out the word hello, that's 5 letters, meaning you've just patterned 5 whole bytes of physical memory.
All right, part 5, pixels and images.
Okay, so that's text. But from words, let's jump over to visuals. Inside a computer, an image is built from a grid of tiny dots called pixels. And just like letters, every single pixel's color is assigned a binary code. Let's say you have a very small image that is 100 pixels wide and 100 pixels tall. That gives you a grid of 10,000 pixels. If we assign just 1 byte of memory to define the color of each pixel, storing that raw image is going to require exactly 10,000 bytes of memory. But think about it for a second. If we only use 1 byte, or 8 bits per pixel, we are totally limited to those 256 combinations we just discussed. That means our image can only display 256 distinct colors. Black would be a pixel where all 8 capacitors are discharged, all zeros. White would be all ones. But 256 colors only gives you a few shades of red or yellow. You absolutely can't show a beautifully smooth transition, like a vivid sunset, with just 256 colors. And that is exactly why modern computers use a 24-bit true color system, assigning 8 bits specifically for red, 8 bits for green, and 8 bits for blue.
And look at this massive leap in scale. By combining those 3 8-bit color channels together, 256 times 256 times 256, modern true color displays can achieve a staggering 16.7 million possible colors. It's a real game changer. Every single pixel on the screen you are looking at right now is constantly mixing 24 microscopic capacitors, turning them on and off in real time just to bring you exactly the right shade of color.
Finally, Section 6, the massive scale. Prepare to have your mind blown as we zoom all the way out from a single switch to the device sitting in your pocket right now. And this brilliantly illustrates the sheer engineering marvel of modern technology. A standard 4 GB RAM chip contains roughly 35 billion of these microscopic transistor capacitor units. Let me repeat that, 35 billion tiny batteries and switches. How is that even possible? Because they aren't the bulky electronic components you see in a hobby shop, they are manufactured at the nanometer scale. Billions of them packed onto a chip the size of a fingernail, all charging and discharging millions of times a second, just so you can casually scroll through a web page.
It really changes how you look at your phone, doesn't it? Every single song you stream, every text message you send, and every compressed JPEG photo you take ultimately boils down to billions of tiny physical switches simply turning on and off. There's no magic in there. There are no floating magical numbers, just beautifully organized physical states. As our source material perfectly concluded, the reward of knowing is knowledge itself. You now possess a truly empowering understanding of the invisible physical world operating silently in your pocket. But I want to leave you with this thought. If a simple 4 GB chip requires 35 billion microscopic switches just to function, what kind of unimaginable physical architecture is going to be required to power the artificial intelligence models of tomorrow?